Hi, I'm Ju Young, and today I'll be talking about this paper called Quantum Computing in the NISQ Era and Beyond. And this was published in 2018. And before I start, actually want to thank everyone for changing the meeting time today on such a short notice. And I would like to give a brief introduction followed by some points on the potential of quantum computing, NISQ computing, and also some potential quantum speedups, then wrap up with a summary. So why did I choose this paper? So today is the first meeting, and I was thinking about what I should present. And the first candidate that I had was a short introduction to quantum computing and information, but obviously there's many good books and papers on this, and I didn't feel qualified enough. So I decided maybe I could talk about something technical. But the problem is today is the first meeting, and we have lots of different people from different backgrounds. So I thought that it would be difficult to find the common denominator. And so I decided to give a broad overview on quantum computing and its development. And I immediately thought about this article. So I want to first talk about why we're all here and why we're trying to study quantum computing. We want to study quantum computing because it's useful in some way. So why is quantum computing powerful? And why is it so difficult to make one? So the author gives three reasons on why we think quantum computing is powerful. The first reason is that we have very good examples of quantum algorithms for classically intractable problems. And the main example that we all know is prime number factorization. So I have some complexity, big O notation complexities here for the best performing quantum algorithm, which is the Shor's algorithm, and the best performing classical algorithm, which is the general number sieve, or on the right, it's denoted as NFS. And we can see that Shor's algorithm has almost exponential speed up over the classical algorithm. And the picture on the right shows that the scaling basically is much better for Shor's algorithm. Don't worry too much about the actual numbers. I'm not really sure about how this actual numbers were created, but you can see the scaling and that the Shor's algorithm has a better, that we can factor larger numbers with less time using Shor's algorithm. So we have these powerful examples, which give some insight into the fact that quantum computing is more powerful. And we also have some complexity theory arguments. So if we think about how classical quantum computing is done, we first prepare an initial state and then we evolve it using some unitary operations, and then eventually we measure the state. And the measurement results follow some probability distribution, which is determined by the circuit and also the measurement basis, or basically how we measure the state. And since we're getting these measurement results from these distributions, we can think of quantum computing as a sampling problem. So a sampling problem is if we have some uniform random bits, we want to change that to follow a certain distribution that we have set. And so there are classes of problems that we can solve with different types of algorithms. So there's a class called SAMP-P. So these are problems that we can solve using efficient classical algorithms. And then there's SAMP-BQP, which is problems that are solvable using efficient quantum algorithms, of course, up to some bounded error. And there are some arguments that show that it seems like SAMP-BQP strictly contains SAMP-P, even for some intermediate scale quantum circuits. And I'm not well versed in complexity theory, so I think that this is about as far as I can explain. And if anyone is more interested in this subject, I have put a reference paper down below. And the last reason that Professor Freskel gives is that there is no known classical algorithm that can simulate a quantum computer. So generally, simulating quantum systems, especially highly entangled systems with digital computers, is hard. And one interesting thing to note, I've added this based on some recent results. Actually, we can simulate quantum computing in time linear with the quantum number and depth if the 2-qubit operation has a fidelity that's less than 1. So basically, if we have a noisy hardware, it's actually easier to simulate something similar to that. And so this is one of the actual reasons that we want to increase the gate fidelity. Of course, there's other reasons, but this is one of them. Okay, so now we have some reasons for why we want to study quantum computing and why we want to make a quantum computer. Then why don't we just make a quantum computer? Well, in order to think about why we can't make a quantum computer easily, we have to first think about what we want a quantum computer to do. So we want the qubits to be isolated from the environment because of the noise. But also we want the qubits to strongly interact with each other. And while doing that, we want to be able to control and measure the qubits reliably. And so if we think about, even if we don't know the specifics of the hardware or physics or the implementation, we can kind of intuitively see that doing these three things at once will be very difficult. And so that is why quantum computing is difficult to implement. And eventually, we want to use quantum error correction. So this is a method of correcting error using entanglement. And we want to do this to eventually make logical qubits that has very low error, or error that we can reduce to such an arbitrary small level. But the problem is that this has a large overhead. So one example is shown on the right. This is called the Shor code. And this large rectangle in the middle is basically the noise channel. It's where the noise is inserted. And in order to protect this 1-qubit state on the top, we use 8 other qubits along with many other gates, including 2-qubit gates and 3-qubit gates. And so this is one example of quantum error correction code, and we can see that we require a lot of quantum resources in order to implement this. And since and since in the near future and right now we don't have a large quantum processors with good gate fidelities, then this will be impossible to implement. So this will not be available soon. Now this leads us nicely to NISQ computing. NISQ computing is noisy intermediate scale quantum computing, and this is a type of hardware that we have right now, and we will use for the near future. And this term was coined by Professor Pascal. So let's talk about the 2 factors in this computing. We have intermediate scale. So the number of qubits that we will have access to will be about 50 to hundreds of physical qubits. And I've brought some examples of some quantum processors that have been announced to the public. So there is a 256 qubit processor from QEra, and a 127 qubit processor from IBM, and a 53 qubit processor from Google, and a 32 qubit processor from IonQ. And actually, one interesting thing is that the way that we make the qubits is different for each one of them. And so for QEra, they used Rydberg atoms. For IBM and Google, they use superconducting qubits. And for IonQ, they use trapped ions. So we haven't even gotten to a consensus to which type of physical implementation would be the best. And the next factor to think about is noisy. So we have noisy qubits without error correction. And in order to talk about how noisy a qubit is, I wanted to give some realistic numbers as to the performance of the qubits. So from the data sheet provided by Google, I've brought some numbers here. So this will be different for each hardware, or like trapped ion will be different from superconducting qubits. But in order to talk about some realistic numbers, I've brought one example here. So for the accuracy of gate performance for 2-qubit gates, the error rate is about 0.7 to 1.9%. And the time to execute gates is about 12 to 32 nanoseconds. And the measurement error of qubits is about 0.5 to 3%. And one thing to note here is that this is the measurement error when we prepared 0 state, but we measure 0 state as 1 state. And actually, the probability for the other way around. So when we prepare one state, but measure it as 0 state is actually higher than this, much higher than this. And also the connectivity for the Weber quantum computer is a grid as shown before. Here, this the one on the third one shows that it's like in a grid form, but this is also very different for different hardware. For example, for the Eagle processor, they use like a hexagonal type of connection, and for the IonQ, I believe they have all-to-all connection. And so on and so forth. There are many different ways and metrics that we can use to talk about about the quality of the qubits. So now we have a sense of why we want to make quantum computers, why making quantum computers is hard, and the type of quantum computers that we have right now. Then I think the next natural topic is what we can do with the NISQ computers that we have right now. And in the paper, many exciting ideas were presented. And when reading it, I think that we have to take into account that this was written, I guess, 4 years ago now. So I would like to focus on just 3 of the topics that Professor Preskill mentioned. And they are quantum optimizers, quantum matrix inversion, and quantum simulation. So I would like to first talk about quantum optimizers. So let's say that we have some optimization problem. Then sometimes finding a good approximate solution itself is actually very difficult. And so we want to see whether or not we can use quantum hardware to find better approximate solutions faster. And one major approach that we're trying right now is hybrid algorithms. So this is like a framework where we have a quantum computer with a circuit that is parameterized by some variables theta. And we measure the resulting state, and using these results, we process it using a classical computer. Maybe we calculate some loss function, and then we use gradient descent on it. And then we get some new parameters to try, and then we repeat this over and over again. And we can use this framework for many different types of problems. And I brought 2 here today. The first one is the quantum approximate optimization algorithm, or QAOA. And this is applying this hybrid algorithm to a classical combinatorial optimization problem. And there's also the variational quantum eigensolver, or VQE. And so this is when we apply this to a quantum problem. For example, trying to calculate the ground state energy of molecules. So we map this problem to the quantum computer. And then from the measurement results, we calculate like an expectation value of the energy. And then if we minimize that, then we can find the ground state energy. And one interesting thing to note here is that since we have quantum test beds, whether that can be classical simulators or quantum hardware, NISQ hardware, this can help us find some heuristic algorithms. So for example, since we had GPUs, we could try out deep learning, and now we're beginning to understand how deep learning works. And we also, for example, for linear programming, before we knew why simplex method was good, we just found out the simplex method. And so likewise, for these types of combinatorial problems or quantum problems, we may be able to use the hardware first to find some good heuristic algorithms and then understand why they work later on. And then the next one is the quantum matrix inversion. So basically, as an input, we have an n by n matrix and vector b. And then the output gives us A inverse times b, up to some small error. And actually, there is an exponential speedup compared to some classical algorithms. But there's, of course, some caveats. So A needs to be sparse and well-conditioned. And B needs to be prepared with something called a QRAM. So it's like an efficient way to load classical data onto as a quantum state. And the output also is a quantum state. So we need to, in order to extract some classical information, we need to measure it. And the circuit diagram is shown on the right. And so the reason that I wanted to talk about this algorithm is that there are sometimes caveats to quantum speedups. So in order to do this, we need QRAM and we also need to be able to think of some nice measurements. And so whenever we talk about quantum speedups, we always need to think about the conditions that we need to satisfy. And actually for this algorithm in specifically, QRAM is kind of difficult to implement, and also these QPE circuits will be difficult to implement also. So we won't be able to use this in the near future. And if you want to read more specifically about the HHL algorithm and caveats, I recommend this paper on the bottom called Read the Fine Print. It's an article written in Nature Physics, and it goes into more detail. And lastly, since I know that there are some physics students here, so I wanted to talk about quantum simulation. So generally, they are difficult for classical computers because the Hilbert space just increases exponentially as the problem size gets bigger. And there's this famous quote by Feynman that says that we basically, in order to simulate quantum mechanics, we need something quantum mechanical to simulate it with. And so this is the basic intuition behind trying to do quantum simulation using quantum computers. And I think that quantum computers are, for simulation, is divided into two. So there's the analog quantum simulator. So basically, it is a simpler system that we can control easily, that has the dynamics that is similar to the real system. And then there's a digital quantum simulator. So basically, this is some universal quantum computer where we can program the gates so that the results is some quantum simulation. And so in summary, right now and in the near future, we will be using NISQ computers. And we have some specific ideas to try to use these computers, like quantum dynamics or optimization. And because of the noise levels, we need some noise resilience built into the algorithms and noise mitigation techniques. And in order to improve the hardware, we need to improve the gate error rates so that when these error rates are below some threshold, we can use quantum error correction to arbitrarily lower the error for the logical qubits. And in doing so, we want to eventually achieve fault-tolerant computing. And so this is an overview of the 2018 paper by John Preskill. And hopefully this gives some background and background into the topics that we will be discussing at EQS for the future. And thank you for your attention. And if there's any questions or things you would like to discuss, please ask in the comments or using your mic. Thank you.
I have a question. So you introduced 4 kinds of physics system for quantum computing, and well, there is no which one is best and which one is worse. But in personal opinion, what do you think? Which system would be the winner of quantum computing?
I mean, I don't think I know enough to say, but maybe superconducting qubits have nice scalability, and there's many companies working on it right now. So maybe it's superconducting qubits.
Okay, thank you. Okay, if you don't have any more questions, let's give a huge applause for Jiyoung for preparing this wonderful presentation. Thank you.